normal approximation to a binomial distribution. And the first thing we need to recognize is that we are dealing with discrete situations. So what we're going to be dealing with is a binomial situation, which means you have two options. You have a fixed number of trials. You have independent events. But the key here, because of the independent events, is that the probability from one draw or one experiment to the next doesn't change. So this is very similar to when we're dealing with the binomial distribution and we're dealing with percentages. But the difference is now we're dealing with counts. So instead of trying to figure out what's the probability of being between 5% and 7% kind of question, we're trying to figure out what's the probability of being at least 5 or no more than 5 or more than 5 or less than 5. Now, you'll notice I have these drawn in, but I'm gonna or typed in, but these two I will draw in a second. So one of the things that has to happen is you've got to make sure that NP is greater than or equal to 10. So I will put the greater than, I will write in or equal to 10. And the same thing with NQ. Needs to be greater than or equal to 10 in order for you to do this approach. Now, before we go any further, I'm going to draw in the z-score formula. This is now, I believe, our fourth of the z-score formulas. Z is going to be equal to. Now, it's going to be x plus or minus 0.5. This little piece here is referred to as the correction for continuity, abbreviated CC. Correction for continuity, and that I'll need to explain. Minus the mean, which when we're dealing with a binomial probability, the mean is going to be NP. And then divided by the standard deviation, that is the square root of n times p times q. Now this is just a modification of the other z-score formula when we were dealing with p hat and p. So if I write p hat and I go minus p from the population, I do the square root of pq divided by n, and this is going to seem a little strange, but what I'm going to do is I'm going to multiply through, well, let me do this real quick just to show you that they are related. Recall that p hat is x divided by n. So where the p hat sits, I have this x divided by n, and then I have this p, and then I have this square root of pq over n. Now, some of this is going to seem a little odd, but what we're going to do is we're going to multiply top and bottom by n, really n over 1. And when we do it in the denominator, what's going to happen is we're going to point out, or we're going to use the fact that n is the same thing as the square root of n squared, because the square root of n squared is n. And the reason I'm doing that, or the reason that we do that, is because then we can take this square root and this square root and we can merge them. And so this is going to look like the square root of pq with an n squared, because the square roots can be merged together because square roots are defined by multiplication and division. And then we have this n in the denominator. Now this n is going to knock off that squared, so we end up with this npq. Well, that's where the npq up here comes from. And when we are dealing with multiplication across addition or subtraction, we have to remember that we distribute. So we're distributing these. And so we end up with n times p, because we have n multiplied by p. And then you'll notice that this n here comes over into this fraction, and then it cancels the two n's out. So you have this n over 1, and these two n's would cancel, leaving you with just the x. Now the reason that we add on or subtract this 0.5 is the following. What we're doing, let me call up a new document here. So what's happening is we have this and we've drawn this before, but basically what's happening is we've got this binomial distribution where we have these probabilities of a 0, a 1, a 2, a 3, a 4, a 5, etc., etc. And they're always discrete values. We're not getting 4.5s, we're not getting 5.5s, we're getting 4, 5, 6, 7, 8, 9, 10, and so forth. And what happens is you have these rectangles, and if you can recall in our world of histograms, our histograms always landed on the half marks. Okay, so just let me kind of fill in a bit here, and I will have, we'll say the mean is 4.5 or 5. We'll do 5. That's fine. And we just work our way back down. Now, what occurs is we end up getting a normal bump in the middle of the graph when our NP and our NQ are both greater than or equal to 10. Now, the reason that we have to add on or subtract that 0.5 is so that we capture the whole rectangle that is above the value that we are working with. So if I said, like I did in this document here that says at least 5, well, if I need at least 5, I need 5 off to infinity. And so what I do is I include all of the rectangle above that number 5. So I'm going to travel back over here, and what I really need to do is I say, oh, I needed to capture all of that rectangle, so I'm going to start at 4.5 and go off to infinity. So if I say at least 5, oops, forgive me, I'm going to put in here, come on, draw, there we go, greater than or equal to 4.5. Now, if I said no more than 5, well, I can't be larger than 5, but I can include the 5. And so, again, I need to have everything from that spot that I just drew, which is the 5.5, back to really negative infinity. So this piece here is going to be less than or equal to 5.5. We have to remember the whole rectangle gets included. Now, if we say more than 5, really, whoops, I have a typo there. I need to fix that. What I'm going to do is, let me get back here, click there, and I say, oh, it's greater than 5.5, because I'm not including the rectangle above the 5, but I need to include the rectangle that's completely above the 6. So here's my 5.5. I'm trying to get all of that rectangle above the 6. And here is going to be less than. So if it's less than, I'm on the left-hand side, and so I'm really looking at 4.5. So here's my 4.5. Okay. So that's the idea of the correction for continuity. And what we do is we're going to plug it in here in our z-score. Now, we need some more information. So now I'm going to type in some more stuff. So we have 20 trials. We can go larger than that. We should go larger than that. Let's say that we have, we'll do 40 trials. Okay? And we are going to say that our probability of success, which is our P, is going to be equal to 0.25. That means our Q is going to be equal to 0.75. Now, we're going to try and find the probability of being at least 5, no more than 5, and so forth. The first thing we need is our mean. Let me back up for a second. First thing we need to do is we need to do NP and NQ and make sure they're both larger than or equal to 10. So 40 times 0.25 is going to be equal to 10. So that one meets and passes the criteria. 40 times 0.75 will be equal to 30. So again, bigger than or equal to 10. And so both of these have been met. And so what we do is to get at least 5, we use this 4.5 in our, click that off, delete that. We need that 4.5 in our z-score formula here. And so what we're going to do is we're going to try and find, let me draw in here, we're going to use, there we go. We're going to have z is equal to, now, we're using 4.5 for the correction for continuity, and then minus our mean. Now, our mean actually is NP, so we just did it up here when we're trying to see if NP is greater than or equal to 10. Works out to be 10. And then our standard deviation is the square root of our n, which is 40, times our 0.25. I dropped the decimal there, times our 0.75. Okay, now, let me type this into the handy-dandy graphing calculator. So, parenthesis, 4.5 minus 10, parenthesis, divided by, second, the square root of 40 times 0.25 times 0.75. And then I hit enter, and my z-score is a negative 2.008. So now we're trying to find out, we're at least 5. Really, we're trying to figure out greater than or equal to 4.5. So, what we do, just a real quick note here. Sometimes they'll drop off this or equal to when you've done the correction for continuity. Just be forewarned, it's okay. You're fine either way. Now, we're going to do second vars, normal, CDF, and our left value will be the negative 2.008. Our upper is going off to infinity, but again, we don't have an infinity button, so we're going to put, a 1 with a bunch of zeros. Because we've put in a z-score, we use the standard normal notation, and we'll use 0 and 1 for our mean and our standard deviation. Okay? Now, I'll just run that real quick. So second vars, normal CDF, negative 2.008, and then the upper is 1 with a lot of zeros. Our mean is 0, and our standard deviation is 1. We go to paste, and we hit 1, and we're at about 97% probability. Okay. Now, you don't need to do the z-score if you remember to do the following for normal CDF. All right. What you're going to do is your lower is going to be 4.5. Your upper will still be a very large number, pretending to be infinity. But your mean is going to be 10, and then your standard deviation is going to be this thing. So the square root of 40 times 0.25 times 0.75. And if you type that in, you should get the 0.97. It works out to be 0.97767. I'll do it real quickly just to double check. So second vars. Oh, sorry. Second vars. Normal CDF. Our lower is going to be 4.5. Our upper is going to be very large. Our mean is 10, and our standard deviation is the square root of 40 times 0.25 times 0.75. And we get, whoops, hold on. If I said this wrong, if I said, for some reason it didn't take 4.5. Hold on. Something weird happened. There it goes. Strange. I'm having a calculator issue. It won't let me type in the 4.5 in the lower. Not sure why. That time it did it. There we go. I see what happened. I put too many zeros down. I've never seen that happen before, but I put too many zeros down in the positive infinity, and it got all weird on me. Okay. So keeping in mind that really what we should be doing is getting the z-score, we can avoid having to do that and spend less time and go straight to the normal CDF. So I'm going to do that. I'm going to go to the normal CDF. Now, my lower is going to be negative infinity because this is no more than. It's to the left. And you're going to ask, well, why don't we stop at 0? Well, it makes sense to stop at 0 from application sense, but we're trying to get the normal curve to approximate it. And the normal curve never ends. So we need a negative infinity in the lower in this case because it's less than. So we're going to put negative 10,000. And then we're going to go up to 5.5. And then we're going to put our mean of 10 in. And then we're going to put our standard deviation, again, of the square root of 40. And then times 0.25. And then times 0.75. And it's going to be a little bit more than 2% is what your result will be. Now, if you're doing more than, so your lower will be 5.5 and your upper will be 10,000, but the rest of it will remain the same. If you're doing strictly less than, then you're using 4.5 instead of the 5.5 in the upper. Okay, I hope that helps and I hope that makes sense. All right, have a good one.